should continue. So next speaker is Jacques Sakarovitch from IRIF, CNRS University of Paris and Télécom Paris. Please, you can go ahead.
Okay, thank you very much. So I'm very happy to talk at this conference. I'm very honored to have been invited, and I thank the organizers. I must say I didn't have the opportunity to meet Boaz Troudenbrot, but so I'm all the more grateful for this opportunity to have at least an intellectual meeting with him. When I was invited, of course, I planned to come to Tel Aviv for the conference, but the course of the pandemic didn't allow it. But I hope that we all be able to meet again soon, and in particular next year at the Automata conference, Jewel of Automata, that will take place in Paris, so in October 2022. So the title of my talk is Derived Term Without Derivation. This probably will not ring many bells to most of the to most of you, but the subject of the talk is certainly one of the most well-known topic in computer science or theoretical computer science. Namely, it's the transformation of a regular expression into a finite automaton. And well, this is probably one very, very classical subject, and and if you have not worked on that subject itself, you probably had to teach it in classes. So this is a joint work with Sylvain Lombardi, and it has just been published in the Journal of Computer Science and Cybernetics, which is probably a rather confidential journal, but you can find it at on archive. In fact, it was a special issue of the GCC of that journal in honor of the founder of the journal. So in the beginning, Kleene created the family of regular events and the family of recognizable events. He established that these two families coincide. He looked at it, thought it was good, and then moved on to something else. I don't think he has ever worked on the subject afterwards, after 1956. In modern terms, I would state this theorem as rat A star equal rat A star. So this is just to set the terminology and the notation. It's very classical, just maybe for the alphabet A, not sigma. And I denote, I don't know whether you see the pointer.
We are not able to see the slides. I think we just see the first slide.
I'm sorry?
The title slide. So
you have not, I mean, the slides are not moving?
Right. Maybe it will work if you share the complete desktop and then not just the particular app.
So you mean you have not seen the screen changing?
Hit Control L. Try Control L.
I did it.
We see just the title slide of the presentation.
Okay.
Now yes.
And if I do that, you don't see it?
Now we see. Now we see.
And you see it changing?
Yes. Try one more.
Okay. Is that okay?
The second slide.
No, we see the second slide now here.
So you don't see it changing now?
No, it's
Oh, it's very strange. Okay, never mind. So now you see it?
Now we see a slide about in the beginning, Kleene created.
Okay. So in modern terms, as I said, so I'm sorry. In modern terms, this can be, I write this rat star equal rec star, And this is just the notation and terminology. So you see the pointer?
Yes.
Okay, so, and it's very classical, but maybe for the alphabet, which is A and not sigma. And I denote because it's lighter and better suited for generalization. The language denoted by an expression, by the expression between 2 bar, and the language accepted by an automaton A between 2 bar as well. Okay. So what a rational, you can take this as a definition. A rational expression is a language, a rational language is a language denoted by a rational expression. A recognizable language is a language accepted or recognized by a finite automaton. And the proof of Kleene theorem can be seen that way. That is, say, if you have an automaton, you can compute an expression that denotes the same language, the language accepted by the automaton. And if you have an expression, you can compute an automaton that accepts the language denoted by the expression. Here, I will be only interested in what's it? I get something. Okay, so I will be interested only on the transformation of an expression into an automaton, and I can even forget about the language. Now, there are two main, I will be interested, there are many more, but I'm be interested in two construction, classical construction. The first one is due to Glushkov, and I call it the standard automaton of the expression. You will see in 1 minute why and how it is constructed. So it's a small automaton. The number of state, the dimension is exactly the number of literal symbol in the expression +1. And the second automaton that is of interest for me here is due to, let's say, a collaboration between space and time between Brzozowski and Antimirov, and I call it derived term automata. And, and later on, there's been a very nice result of Champano and Ziadi connecting these two automata, saying that, in fact, this derived term automaton is a morphism, is morphic image of the standard automaton of the expression. Well, to make a long story short, morphism, just SE, you can say it's a simulation of the derived term automaton, or so you can merge states of the standard automaton to get the derived term automaton. Okay, and the topic of my talk is to give you a new definition, a new construct, not new definition, new construction of this derived term automaton. But to explain that, I have to go back to the construction both of the standard automaton and of the classical construction of the derived term automaton. So an automaton, well, it's a label directed graph, which I prefer to write with the matrix expression. So E is the matrix, the transition matrix of the graph, and I and T are two Boolean vectors that represent the initial state and the final states. A standard automaton is an automaton with one initial state only, with the property that no transition is the destination of that initial state, which means that in the matrix representation, the initial vector has only one non-zero entry, and that the transition matrix at the first column, which is all 0. And the interest of the standard automata is that you can define operations, the rational operation on these automata, A plus B, AB, and A star, And this is very easily described with a matrix representation. So this is the description of the addition of the two automata. And of course, the language accepted by the sum of A and B is the union of the language accepted by A and the language accepted by B. Similarly, you have a very simple formula for the product of the two automata and a formula for the star of the automata. And of course, what is interesting is that the result of this operation on standard automata gives you standard automata. That is, so you can iterate this construction. And that's what we'll do to define the standard automaton of an expression. We start from the base cases, of course, on the matrix form, and then very naturally, the standard automaton of the sum is the sum of the standard automata, and the same for the product, the same for the star. And this gives you the definition of the standard automaton of an expression by induction on the formation of the expression. And it's more, it's not only the definition, it's in fact, to my knowledge, the best algorithm for constructing this standard automaton. And it is the one that we have implemented in our system hourly for the computation of automata. And this system is also recently put in the public. Now, so this is where we are. And now the second thing is, the second automaton I want to describe is the Brzozowski automaton. So we start with first, somehow Brzozowski started from the definition of the minimal deterministic automaton of a language. So this is more or less common knowledge. The minimal automaton is the states of this automaton are the quotients of the language, and it's a characteristic property of recognizable language that it has a finite number of quotients, and out of these states you make easily an automaton that constructor. And so the idea of Brzozowski was to lift this construction of the minimal deterministic automaton on the set of expression. So he started from an expression that denotes the language, and he defined an expression which he called the derivation of the expression that denotes the quotient. And using this construction, he was able to build an automaton, a deterministic automaton that accepts the language. So if we have just a look at the definition of the derivation, so it's by induction on the formation of the expression. And what is interesting in this formula is that the derivation of the sum is a new expression, which is the sum with the plus operator of the derivation of the first term plus the derivation of the second term. And so this is the way you compute the derivative, one derivative of the expression, the derivation by A. And you compute all derivatives by induction on the words. And there is the theorem, the result of Brzozowski is that you have a finite number of such derivatives, not exactly a finite number of derivatives, but if you take these expression modulo the associativity, the commutativity, and the idempotency of the plus operator, that is E plus E is equivalent to E. And so this gives, let's say, the derivative automaton of Brzozowski. This automata, this was a very nice idea. I have no time to elaborate on this, but it had two drawbacks. First, it's a large automaton because it's deterministic. So it's potentially exponentially larger than the standard automaton. And the second thing is computationally, it's not so easy to compute because you have to compute these expression modulo equivalence, and this is not so easy. And then came the idea of Antimirov. The idea of Antimirov was very simple, although it just replaced the plus in the construction of Brzozowski by a union. And this simple idea was sufficient to make things much simpler because the union itself takes care of the associativity and of the commutativity and of the idempotency. And so you have to define the union of the derivation of a union and the derivation and also the product of a union by an expression, that's very easy. And then you compute the derived term, you can make this derivation for every words. And so, and I call these expression you get in that way derived terms. In fact, the original terminology by Antimirov was partial derivatives, which was very, not very good idea because derivative is also already a partial derivation because it's with respect to one letter and you have many letters. So let's stick. And so, and this number is a very small number of derived terms. So it's less than the number of derivatives of state of the standard automaton. And if we go back to our schema, so the derivation of an expression becomes the union of several expressions, and the union of the language that you know gives you back the quotient, and then you build exactly the derived term automaton in that way. So now we have this derived this situation, and then so there was later the result by Champernot and Ziadi saying that these two automata are related. Now, to tell you why we wanted to change the definition of the construction of this derived term automaton, first you have to understand that this construction does not generalize to other monoid than the free monoid. So if I take a non-free monoid, I can define, but just think of let's say A star cross B star. That's, for instance, if you're dealing with a transducer relations between one free monoid to another monoid. So the point is now it's not true anymore that the rational sets of the monoid are equal to the recognizable sets, where when you say that the recognizable sets are those that have, let's say, a finite number of quotients, let's say. Nevertheless, you have a theorem that you cannot call a Kleene theorem, but we tell you that the language that are denoted by an expression are exactly the language that can be recognized, but that can be accepted by an automaton, exactly in the same way. And so you have the same thing for, you can build standard automaton exactly in the same way, by same result by Glushkov. You can say you can extend this construction to any monoid. But of course, you cannot extend the construction of the derived term because the construction, the derivation, and the proof that the automaton accepts the language denoted by the expression relies on the quotients of the language by letters and by words. So there are this construction can, of standard and of derived term can be generalized to automata with multiplicity, but I have no time to get to that. But in fact, this generalization, which I did with Sylvain, was not so easy to do. And in fact, we were led to compute the derived term independently of the derivation. And so this was the starting point of the new construction. So if you have, so what we did was to define the derived term by a pure induction on the formation of the expression. So these are the formula, very simple. That is the derived term, the base case are obvious. And the derived term of a sum is the union of derived term, and the derived term of a product is something quite rather natural for some derivation with respect to a product. And the derived term of the star is given by this formula. And by induction, we see that the number of derived terms of an expression is less than or equal to the literal length of the expression. And now this, in fact, now the new thing is that using that definition, we will be able to build a new automaton, which we call not the derived term automaton, but the standard derived term automaton. And this construction will be by induction on the formation of the expression. And this standard derived term automaton will have two properties. The first property is that its dimension is exactly the direct, disjoint union of the expression and the derived term of the expression. And in fact, the expression will be the initial state of that standard automaton. And the property that every step will see that there is a morphism from the standard automaton to that standard derived term automaton. And okay, the base case to begin with, it's obviously, it's very simple. So we start back for 0, 1, and for 1 letter, the standard derived term automaton is equal to the standard automaton. Now for the addition, so what we have is it's easy to compute the sum of the two standard derived term automata, because we suppose that we have a standard derived term automaton for F, a standard derived term automaton for G, and we can make the sum. And because of the formula we have seen before, so the dimension of this sum is this disjoint union of E with the derived term of F, disjoint union with the derived term of G. And of course, so now I recall how you get the derived terms of expression. So you have a natural map from the set of states of the sum TF and TG plus TG onto the set of derived term of F plus G, because if there is one common derived term between F and G, then phi will map them, map on the same element. And the key property, and this is somehow the substance of the construction, is that map phi is a morphism of automata. And this is, of course, it has to be proved. And with this property, we can define what will be the standard derived term of the sum. It will be the image by this morphism phi of the sum of the standard derived term automata of F and G. So, and afterward, there is somehow it's an easy lemma or ancillary lemma that said that, of course, okay, the morphism, if you have two morphism between standard automata, you get a morphism on the sum, and this ensures you that the property 2 will be fulfilled, will hold for the sum. And now somehow the product is treated about the same way. So you form the product of the standard of the two standard derived term automata, and you have a natural map from the set of states of the product of the automata onto the set of states of the derived on the derived term automata of the product. And the key property is that this map psi is a morphism of automata. And so you have, so you take as a definition of the standard derived term of the product, the image by this morphism of the product of the standard derived term automata. And again, you have a lemma that ensures you that the property 2 will hold. And now for the star, it's easier because the dimension of the star of a standard automaton is the same as the dimension of the automaton you started with. And so you just need a lemma to ensure you that the property will hold. And so this is sufficient. So we have the base case, we have the construction for the 3 rational operators. So we have, by induction on the formation of the expression, we have the construction of the standard derived term of automaton of any expression E. Now we are not completely, the construction is not complete. So now we want not the standard derived term automaton, but the derived term automaton. And we have again a natural map from the disjoint union of E and the derived term of E on the union of E and the derived term of E. That is, if E is a derived term of itself. And we have another proposition, which is much easier to prove, that this natural map is again a morphism, and by definition, not by definition. So the derived term automaton, I don't know why I have this name, is the image of the standard derived term automaton by this natural map. Okay, and so So we get back to the figure that is, so we have been able to build a derived term automaton, even in the case where the monoid is non-free. And so, of course, I mean, in the case where the monoid, the base monoid is free, so we have not changed the object. We proved that, of course, this automaton that we have built is exactly the same as the one that was built by the construction of Brzozowski and Antimir. And this is, I will stop here and I'll be happy to answer the questions.
Thank you. Question by Moshe? Yes, go ahead. You should unmute yourself.
You're mute, Moshe. And we don't see you.
Okay, can you see me now?
Yeah.
Can you hear me now?
Hear you. Yeah.
Okay. Well, thank you for going back to early stuff that I need to go back and look at. But you keep using the term automata, automaton. And in my world, I usually say NFA, DFA. So which part here are deterministic and which part are non-deterministic?
Well, for me, okay, automaton, okay, I use automaton for NFA. And that's the model. That is finite directed labeled graph. And deterministic is a subclass of it. Okay.
But Brzozowski was about generating a DFA, right?
Yeah, that's what I said. Yeah.
Okay, okay, now I understand you. Thank you.
Maybe I was not clear enough.
No. It's perfectly. Now everything falls into place for me. Thank you.
Okay, so that was somehow, I mean, I talked with John. So he had really, he wanted to leave the construction of the minimal deterministic automaton to the level of expression, because he wanted somehow, he wanted to be able to prove the equivalence of expression within the realm of expression. But in fact, what he was doing was he built an automaton. So he acknowledged that. But okay, it was a very smart idea. And not obvious, because it has to consider this expression modulo, okay, these identities, commutativity, and of addition and idempotency. But well, he told me at the time he was working on it, at the beginning, in the early 60s, a real automaton was a deterministic automaton. NFA was weird objects somehow.
Interesting.
Thank you. More questions? If not,